Question: what does intelligence, knowledge, news, communication, and data have in common? If we quickly first define intelligence on Google, we get this. Intelligence. 1. The ability to acquire and apply knowledge and skills. And number 2, the collection of information of military and political value. So, intelligence is related to acquiring and applying knowledge. In its second definition, intelligence is related to information collection or gathering. Now, if we define knowledge, it says, knowledge. 1. Information, facts, and skills acquired by a person through experience or education, the theoretical or practical understanding of a subject. Also, if you look below, it says, what is known in a particular field or in total, facts and information. Now, let's define news. News. Newly received or noteworthy information, especially about recent or important events. And below says, information not previously known to someone. And as for communication, the imparting or exchanging of information or news. And below, a letter or a message containing information or news. And number 2, the means of sending or receiving information such as telephone lines or computers. And finally, data, which is the plural form of the singular datum. Facts and statistics collected together for reference or analysis. And below, you have datum, which defines as a piece of information. And now that we have those 5 definitions, what does intelligence, knowledge, news, communication, and data have in common? As you may have noticed, they all contain information. Matter of fact, pretty much everything contains information in this information age. So what is information? Yes, what is information? As simple as it sounds, it's most likely not what you think it is. But let's first see again through Google. Information. Facts provided or learned by something or someone. Okay? Look at this one. What is conveyed or represented by a particular arrangement or sequence of things. That's really interesting, but not clear. And below this, in information theory, a mathematical quantity expressing the probability of occurrence of a particular sequence of symbols, impulses, etc., as contrasted with that of alternative sequences. The first definition is very general, but not exactly what information is. And the second one is very interesting, but it isn't very clear because what is conveyed is usually the message, and the message is not the medium in which it was sent. I'll be coming back to that later, inshallah. And note below, in information theory, it is a mathematical quantity expressing the probability of occurrence of a particular sequence of symbols, impulses, etc., as contrasted with that of alternative sequences. This definition is very true in computer science, as this definition is based on Shannon's entropy equation, which provides a way to estimate the average minimum number of bits needed to encode a string of symbols, based on the frequency of the symbols. I'll be coming back to that later as well, inshallah. But note, this definition is an information theory, and information is a theory for a reason. And a theory is a supposition or a system of ideas intended to explain something, especially one based on general principles independent of the thing to be explained. And a supposition is an uncertain belief. Matter of fact, information contains a lot of uncertainty. Although we all seem to have an idea of what information is, however, it's nearly impossible to define it clearly. Here, let me demonstrate what I mean by that and why information is a theory. Let's say we have a USB key with 1 exabyte storage space or memory. By the way, there's no such thing as a 1 exabyte USB key or flash key or a secure digital card, SD card. It's currently impossible to manufacture because 1 exabyte is 1 quintillion bytes. The symbol for exabyte is EB. 1 exabyte is 1000 to the power of 6 bytes, which is equal to 10 to the power of 18 bytes, which is basically 1 with 18 zeros, bytes. Or 1000 petabytes, or 1 million terabytes, or 1 billion gigabytes. Hence, an exabyte is huge. And a Google is 10 to the power of 100, which is where Google got its name from. Google, however, stores much more than a Google. the corporate headquarters complex of Google is called the Googleplex. And a Googleplex is also a number which is 10 to the power of a Google. So 10 to the power of 10 to the power 100. A Googleplex is so enormous and incomprehensible that if you write a book with a number 1 and then a Googleplex of zeros with the font size of 1, the amount of physical books to print so many zeros will not even physically fit in our entire observable universe. That's how huge a Googleplex number is. Thus, Google and its headquarters, the Googleplex, is based on this number because Google stores enormous amounts of data, information. That's why some mathematicians say that there is no need to go near infinite, as gigantic numbers are already incomprehensible. So back to why information is a theory with the imaginary 1 exabyte USB key stick example, which can hold about 300 million hours of good quality video. So for the sake of this example, let's say you have a futuristic 1 exabyte USB drive like this. And then we weigh this 1 exabyte USB key stick or drive while it's empty, meaning there's zero information in it. So the balance tells us that the 1 exabyte USB key stick weighs about 19 grams. Now, if I plug the 1 exabyte USB key stick into a 1 zettabyte hard drive and then fill up the 1 exabyte USB key stick with 1 billion gigabytes, so which is equal to 1 exabyte, of information. So the 1 exabyte is completely full of information. In other words, I just filled up the empty 1 exabyte USB key completely. The question I have for you is, will this 1 exabyte USB key stick completely full with information be heavier than an empty 1 exabyte USB key stick with no information? So will it be heavier or not? In other words, will the 1 exabyte USB key stick weigh more than 19 grams if it is full of information? Remember, 1 exabyte USB key stick or flash drive completely full is like having 1 billion gigabyte USB drives full of information. So I'll give you a few seconds to think about that. If you thought it's heavier when it's full, then you're wrong. But if you answered they have the same weight, then congratulations. You are correct because whether the USB key is full or empty, it will weigh the same. So the example of the 1 exabyte USB drive being filled up with information or empty, they both have the exact same weight. That is because information is massless. It cannot be weighed. It's in its own invisible field. Mass is a property of physical objects from subatomic particles to clusters of galaxies. In contrast, information is an abstract concept, not a real physical object, so it cannot have mass. Although it doesn't have mass, we can encode information on physical objects in many ways. These physical objects are the mediums. The mediums are things we encode the information on. For example, a piece of paper, a book, or a hard drive, which usually have mass, but this mass is not the mass of the information itself, nor is there any correlation between the amount of information encoded on an object and its mass. For instance, if I carve my name or any word on a tree or a rock, I actually reduce its mass. Think about that. There will be less mass on the medium. However, if you write the word bird with ink on a piece of paper, but a bird is not ink or paper, and ink and paper are not a bird, obviously. The paper itself is not the information. The information is represented in the pattern of ink symbols that lies on the paper's surface. Thus, in this case, ink and paper, to create the information, you have to add material. Information must not be confused with meaning. For example, two messages, one of which is heavily loaded with meaning, and the other of which is pure nonsense, random, can be exactly equivalent as regards to information from the present viewpoint, same amount of letters. The semantic, meaning of language or logic, aspects of communication are irrelevant to the engineering aspects. In other words, the message and the medium are not the same thing. The medium is not the message. The medium, book, paper, ink, USB key, etc., carries the information, but it is not the information or the message itself. The message can be sent in many different forms with the exact same information. This is why information is a theory. Pretty strange, huh? It will get even stranger later on. So keep that in your mind. But if information is a theory, then is information real? It definitely is real, because it can have a direct impact on you, like reading a negative or positive comment. The fact that you are watching this video is real because the massless information, like light, is transported through these physical mediums, and we process it in our sophisticated minds that God, Allah, gave us. Allah, God, also gave us one of the most amazing tools, our hands. With hands, we are able to make other tools that benefit us in many ways. Besides having clothes on, this trait of making tools to make tools and use other tools is what distinguishes us in our intelligence versus all other creatures, not including angels or jinns or crows. Because of our current understanding of this mysterious nature of information, we have created powerful tools that enable us to transport, manipulate, encode, and decode information through nano-sized transistors. And these tools are computers. Computers, as you are aware, are powerful tools because they can process information with incredible speed, accuracy, and dependability. They enable users to access information whenever necessary and to share information with other users. They allow people to use the internet, by God's will, just like watching this video, which is a global network connecting millions to billions of individuals, educational institutions, businesses, and government agencies. Computers can efficiently perform input, output, process and store operations, and they can store massive amounts of data. In other words, information. Storing massive amounts of data or information is memory management. Memory is one of the most important requirements in computers, and it is also vital for any creature, especially us humans, to remember. That's right. Without memory, we will not be able to remember. Memories makes us who we are by Allah's will. And memories contain information. Thus, we are informational beings. One of the most sophisticated areas we process information is in our brains. Our brain is like another tool, and the most advanced computer is still no match for the human brain. It takes 82,944 processors and 40 minutes for a supercomputer to simulate a single second of a human brain activity. These are 2017 statistics. Our brain contains around 100 billion cells called neurons, the tiny switches that let you think and remember things by Allah's will. Computers contain billions of miniature brain cells as well. These computer neurons are called transistors, and they're made from silicon, a chemical element commonly found in sand. Transistors have revolutionized electronics since they were first invented over half a century ago. In simple terms, transistors can do two things. They are amplifiers and switches, like light switches. You can turn them on and off. And as amplifiers, it takes in a tiny electric current at one end, an input current, and produces a much bigger electric current, an output current, at the other. In other words, it's a kind of current booster as well. That comes in really useful in things like hearing aids, one of the first things people use transistors for. A hearing aid has a tiny microphone in it that picks up sounds from the world around you and turns them into fluctuating electric currents. But what I want to focus on are the tiny transistors, the tiny switches. A tiny electric current flowing through one part of a transistor can make a much bigger current flow through another part of it. In other words, the small current switches on the larger one. This is essentially how all computer chips work. So a memory chip contains hundreds of millions or even billions of transistors, each of which can be switched on or off individually. Since each transistor can be in two distinct states, it can store two different numbers, 0 and 1. With billions of transistors, a chip can store billions of zeros and ones. So, when a transistor is on, it's a 1, and when it's off, it's a 0. The computer mind is like a long chain of ones and zeros constantly calculating, concatenating, and computing. And in order for a computer to calculate or compute with ones and zeros, it must reckon with the base 2 system, the binary system, zeros and ones, which is why a computer is called a computer. It computes ones and zeros. To compute with binary numbers may seem a bit complicated at first, but there's actually a simple way to learn this using an amazing tool God, Allah, gave us, and that is our hands. That's right. You can count in binary with none other than your hands. To be more precise, by using all 10 fingers in both hands. This is called binary fingers. Forget about counting to 10 with your fingers. You can count past 1,000 if you want with 10 fingers. Now, if you want to participate, please do if you want to better understand binary numbers and a very important logical system. All you need is a pen, or you can imagine the numbers by looking at the screen. So first open your right hand in front of you with your right thumb facing right like this. And on your right hand, write with your left hand the number 1 on your right thumb, and then the number 2 on your right index finger, and then 4 on your right middle finger, and then 8 on your right ring finger, and finally 16 on your right pinky. So your right hand should look like this. Binary numbers are written from right to left and not left to right like ordinary numbers. That is very important to keep in mind, and that is why you see a 1 on your right thumb. And then towards the left, the next binary number 2, and then it continues to multiply by 2 till your pinky. Now this is how your fingers represent ones and zeros. When any finger is unfolded, opened, or pointing out, it represents the number 1. And whenever a finger is folded, closed, or curled into your palm, then those folded or curled fingers represent zeros. So 0 or zeros looks like this. All fingers are folded, closed, and curled into your palm. And the number 1 looks like this. 1, 0, 0, 0, 0. And the number 2 in binary looks like this with your right hand. Notice your thumb, the number 1 is folded and your right index finger is unfolded, opened and pointing up. So you have 0, 1, 0, 0, 0, or simply 1, 0. 1, 0 is the number 2 in binary. All you are doing is adding the digits on your fingers to represent binary numbers, ones and zeros. And whichever finger stays pointed up is a 1. And if your fingers are folded, then 0. You may have noticed that there are no odd numbers besides the number 1 on your fingers because binary numbers are even numbers. If it isn't clear yet how binary fingers work, then the following questions and examples should make you understand it better. So my question to you is, how do you add with your fingers to make the number 3? And the fingers that you add up to make 3 remain open and pointing out. And the fingers you do not need to add up to 3 remain folded, closed like a fist. Now, this is the purpose of why I'm getting into this. There is only one option or logic in order to add with your fingers to make the number 3. And that is by adding your thumb and your index. And that addition looks like this. And since 2 fingers are unfolded and they represent ones, you have 2 ones like this. 1, 1. Or the number 11 is the number 3 in binary. We'll do a few more until you get it, inshallah. We'll skip the number 4 and 5 as they unfortunately seem vulgar. So, how would you make the number 6 in binary digits of zeros and ones with your fingers? So look at your right hand and find what numbers add to 6, and you will only find one solution. Did you find it? Your index is 2, plus your middle finger, which is 4, and they sum up to 6. And the number 6 in binary numbers looks like the peace symbol with your fingers. And when you write this in binary numbers, it gives you 110 because your index and your middle finger are unfolded, representing a 1 each, and your thumb is folded, which represents a 0. And that's how you get 110, or 110. Remember, this is a lot easier if you have written each number on your finger. Here, let's do a little harder example. How do you make the number 19 with your fingers? So again, look at your fingers and find the closest number to 19, which is 16, your pinky. So close all your fingers except for your pinky, which looks like this. And now ask yourself, how much are you missing to make 19? 3, right? So how do you make 3? Just like we saw before, 1 is your thumb, plus 2 is your index, which equals 3. So your hand looks like the Spider-Man's web swing or the rockstar sign, which is the number 19 in binary fingers, but in binary numbers, it is 11001 or 10,011. Know that these are just fingers representing ones and zeros, and not to be confused by false symbolism. Note that there is no other way to make 19 with your fingers. There is only one option, and that's what makes binary numbers so efficient. Thus, when all your fingers are pointing out, or unfolded, or opened, they represent the number 1. And whenever a finger is folded, closed, or curled into your palm, then those folded, curled fingers represent zeros. So the maximum number you can make with your right hand is 31, which is basically like showing a high five like this. And 31 in binary digits is 11111, because all 5 fingers are unfolded. Here's a chart of all 31 numbers with your right hand. Recall that a memory chip like a USB key contains bytes, plural, a group of binary digits or binary bits, usually 8, operated as a unit. So each finger on your right hand acts as a bit, a 0 bit when your finger is folded, closed, and 1 bit when your finger unfolds, opens. Hence, your right hand has 5 bits of information in regards to binary bits. But if you add your left hand, you can add another 5 bits by continuing the sequence of binary digits as you multiply by 2 as shown here. Therefore, you can now count past 1000 if you want, if you leave all 10 fingers open like this. Yeah, 11111, 11111, which equals to 512 plus 256 plus 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which equals 1023. As a result, you should now know how to count binary, as it is very logical, and you should now realize that each binary number is unique and can never be confused with another binary number, as there is only one option to make every individual number, thus making it very precise, effective, and efficient. Did you notice the numbers your fingers make? Your cell phones may have 16 gigabyte or 32 gigabyte or 64 gigabyte, etc. With SD cards, a lot more. These numbers should be familiar as they are binary numbers. Therefore, with 10 fingers, you have 10 bits which can count till 1023. However, you can take this to another level if you flip your hands the opposite way, as if they were on the table like this. You can continue the binary sequence from your right pinky, which will have the value of 1024. This will act as the 11th imaginary finger. These imaginary fingers will include the following binary values: 1024, 2048, 4096, 8192, 16384 for the backside of your right hand. And from the left thumb, the binary values continue: 32,768, 65,536, 131,072, 262,144, and 524,288. This is very difficult, but it is possible to imagine all 20 fingers lined up next to each other, which will look like this. This sums to 1,048,575. Hence, you can count over 1 million bits with your fingers. So 8 fingers are equal to 1 byte. Note, every digital information are in bytes, megabyte, gigabyte, etc. So these 1 million bits of information that you can calculate with your fingers equals to 125 kilobytes. Now imagine each one of your binary fingers are like transistors. Unfolding and folding your fingers are like transistors turning on and off, but much tinier. So tiny that as of 2016, modern silicon commercial transistors are smaller than 45 nanometers in size. And they are just getting smaller that, as of 2017, NVIDIA's Tesla V100, an enterprise-level processor powered by the Volta GV100 GPU, the first chip in the world built with a 12 nanometer FFN, a FinFET NVIDIA. Process packs in 21.1 billion transistors, one of the most ever jammed into one chip. Here's what 1,800,000,000 transistors look like. 5 nanometer scale devices have also been commercially produced, and we have currently arrived at 1 nanometer transistor, but not in mass production. A sheet of paper is about 100,000 nanometers thick. A strand of human DNA is 2.5 nanometers in diameter. These transistors are so minute that they're invisible to our eyes, but they are very real. These tiny little zeros and ones are turning on and off in mind-boggling speeds, while being invisible, and the information they carry are invisible and massless as well. Subhanallah. It's quite incredible how a computer chip at the heart of your smartphone or PC really is. In the case of a smartphone, you essentially have a single less than a square inch package that enables you to do almost anything, from playing games to accessing a cellular network, watching videos, photos, and to contactlessly pay for your groceries. To do this, those billions of tiny switches inside each chip switch on and off up to 4 billion times per second. And without memory, none of this can be performed. Thus, memory is key. So a memory chip contains hundreds of millions or even billions of transistors, each of which can be switched on and off individually as well. And the way memory works is similar to the way the most advanced transistors work, which is by controlling the movements of individual electrons. A certain very low voltage represents 0, and another voltage, a bit higher, represents 1. As you can see, there's many ways to represent on and off, high and low, 1 and 0. ASCII is the standard computer mapping between ones and zeros and the English alphabet. A equals 1000001, capital A. That means when you punch the letter A, like Allah, on your keyboard, the keyboard sends a 1000001 to the computer. On the other side, 1000001 is interpreted as a capital A and displayed on the screen. Ones and zeros themselves are in turn coded into a series of electrical impulses or magnetic bits on a hard drive. 1000001 might be stored on your hard disk as north versus south spots of magnetism. In other words, 1000001 is NSSSSSN. That's another way to represent on and off, high and low, 1 and 0. Magnetic storage or magnetic recording is the storage of data or information on a magnetized medium. Hard drives use magnetic memory to store giga and terabytes of data, information in computers. So, when I type the capital letter A, it is not an electrical impulse, nor is it a magnetic field. The electrical impulse or magnetic field represents A. This is what is meant when we say the message is independent of the medium it's stored in. Hence, the medium is not the message. However, the medium can affect both the form and the content of a message. The medium is therefore not simply neutral in the process of communication. Additionally, the medium in this case is the hard drive, and the hard drive is part of the hardware. The hardware is like your brain. Your brain contains an average of around 100 billion neurons. So your brain is like a super highly advanced hard drive, just like the physical part of the computer, in other words, the hardware. Software, on the other hand, is like the mind. The brain and the mind are two different entities. Just like computers, hardware and software are two different things. Software refers to the code that runs on the computer. To get a clear picture, hardware is the physical stuff inside a computer and the peripheral devices connected to it. Software is the electrical signals which tell those devices what should be done and when. In general, these things are referred to as programs, in that they program the hardware into understanding what its purpose is. These are usually saved for later reuse instead of having to make them from scratch each time. In order to save these, some other hardware is used. For example, a hard drive which saves such, and can later recall them, as spots on a magnetic coating. So that's a summarized way of how 1000001 is interpreted as capital A and displayed on the screen. Technology is being used on a regular basis, and you should know that it's based on logic and not magic. And God knows best. But what is your phone or computer without a screen? It would be pretty useless, right? And that brings us to the screen. Before we explore the hidden doors of the Quran Cipher 19, as this will galvanize your mind a bit more with important information. The screen is really an engineering marvel of our time, as it is filled with thousands or millions of tiny pixels in a two-dimensional flat surface in which you are looking through to watch this video. Alhamdulillah. You probably heard about taking a screenshot with your phone. You can do the same thing on almost any computer. Usually, on the top right near the delete button, there's a button called Print Screen. As soon as you press a Print Screen button, Windows will grab the color number of all of the pixels on your screen, little dots, and save it to your clipboard, where everything you copy Control-C goes. So you can paste it in Paint, or whatever program you prefer. Then the information can be transferred to a USB key in zeros and ones encoded. So here, let's look at this image of a Kufic-style Quran. Once I press Print Screen, it is saved on my clipboard, just like if I press Control-C. And now I can paste it in, let's say, Microsoft Word, a software program. Note, when you press Print Screen, everything on the screen is copied. Thus, each pixel has a specific color information. Each color information, or pixel, is connected to a transistor, and each transistor is converted to bits of zeros and ones. You are therefore looking at a map of bits of zeros and ones. This is known as BMP, bitmap. The name says it all, a map of many bits, a map of tiny zeros and ones, bits of information. Your screen is kind of like an illusion. It can show a three-dimensional image from a two-dimensional screen bitmapped with zeros and ones being manipulated by only three colors that have many shades. And this image or images you see are known as raster images or raster graphics. Raster images are stored in image files with varying formats. Thus, when you are looking at a digital screen, you are looking at a bunch of tiny zeros and ones. And since they are so tiny, our monitors only properly work for humans. And if an animal sees a computer screen, it doesn't see the same colors as you do. Monitors work based on an optical illusion that is specific to humans. It's an ingenious optical illusion that only perfectly works for humans, not for animals. Now, bitmap or raster are not the only format images can be rendered. There are also vector images or vector graphics. Vector images are mathematical calculations from one point to another that form lines and shapes. And if you zoom into a vector graphic, it will always look the same. The math formulas stay the same, rendering the same visual graphic no matter the size. Vector graphics can be scaled to any size without losing quality. This is important to note because I will be zooming into the Quran soon. So, for pictures, bitmap raster is best, and for text, PDF, Word, etc., vectors are best. Digital zooming is truly an amazing tool that we have. So this print screen of the Kufic Quran can be transferred and stored into a USB key. Now remember, a full USB key is no heavier than an empty one. What was this massless information that was carried and transferred? A print screen of the Kufic-style Quran image that was saved into a USB key. This is how we are digitally communicating in the tiny unseen, the invisible. Although with the right tools, they are clearly visible. Now, the point that I want to come to is this. Let's completely digitize the Quran. What you are looking at are all the verses in the Arabic Quran. This is the whole Quran in one page. This is the tablet, Lawh. And you'll know why.